Good day, one and all. This video is being made to explain chemistry concepts needed by pharmacy students, and it's an initiative from the GPAC University Academic Board. This lesson will focus on Pharm 151 chemistry. That will be inorganic and physical chemistry. Now, this lesson will actually focus specifically on three concepts: solvent effect on acidic strength, ionization concept, and ionic product of water. Good. Now, these are references for further reading. So we start electrolyte. Now, even when you hear the name electrolyte, it should actually signal that then we are talking about electrons or electricity, and then the light might show you that it's a fluid that we are talking about. And then if you have that assumption, you are actually right. When we mention an electrolyte, we are talking about any solution. The solution can be a metal in the molten form or an aqueous solution, as this definition has stated here, that can conduct electricity. So aqueous solution or molten solution that can conduct electricity is an electrolyte. Now, we have two categories of electrolytes generally. We have a strong electrolyte, which will produce a large number of ions in solution, and we have a weak electrolyte, which will produce weak or small number of ions in solution. Now, what will make an electrolyte strong is usually a full dissociation. So we have to take note of this, that the electrolytes that we consider as strong ones, they can dissociate fully to produce more ions. And so if you take a salt like NaCl, we consider this as a strong electrolyte because it can dissociate fully to give me Na plus ions and then Ca minus, Cl minus ions in solution. Now, if we see the electrolyte is weak, it means it can only dissociate partially. And then we'll talk about more of these equations as we go along. So something like acetic acid, it can only dissociate partially to give me few of acetate ions in solution and then few of protons or hydrogen ions in solution. So because they produce a little amount of ions, their conductivity is also small. And then because these ones produce a lot of ions, their conductivity is actually high. Now, I think by now you should know that the reason why some of these solutions or all these solutions are considered as electrolytes is because they have ions. And so if a question comes and then a solution is not an electrolyte, one of the things that should trigger is that it cannot conduct electricity, firstly. The next one is that it cannot produce ions, because an electrolyte should be able to conduct electricity, basic function. And then the next one is that it can only conduct electricity if it has ions, mobile ions for that fact, inside. Now we have solutions that cannot conduct electricity, and then we call them non-electrolytes. And then they cannot conduct electricity because they have no ions dissolved in them. A classical question that comes at this point is, we can give you a compound like this, HCl. Now, the pure HCl liquid cannot conduct electricity. It is not an electrolyte, so we call it non-electrolyte. Now, the HCl same compound in an aqueous medium, that is in water, is an electrolyte. And so we ask ourselves, why is this one not an electrolyte, and then why is this an electrolyte? You might not really know what is going on at the molecular level, but then I think the two things that you should be able to say is that this is an electrolyte because it can conduct electricity primarily, and then you should know that it is, once it's conducting electricity, it means that it also has ions inside. That means it can produce ions, right? Good. So these should fetch you some marks, and then if you want further knowledge, or if you want to throw more light on the concept, then you tell me that HCl can dissociate in water to produce the H plus ions and then the Cl minus ions. So what is making this act as an electrolyte is that water will allow the HCl to break down, and then it breaks down into H plus and then Cl minus ions. Now these ions will be responsible for the conduction of the electricity. So that is that for that. Now, compounds which are electrolytes are generally acids, bases, and then salts, right? Good. Now, most of the salts we know are fully soluble in water, and hence are considered as strong electrolytes. The acids which are strong acids, that's the ones that can dissociate fully, are also considered as strong electrolytes. Example, H2SO4, HNO3, HCl, HBr, and HClO4. Now, the strong bases, that's the bases that can also dissociate fully, are also captured as strong electrolyte. Examples are NaOH, KOH, CaOH2, BaOH2. So these are strong electrolytes. We should roughly keep some of the examples in our head, about 3 of them. Now, the ones that can dissociate partially to give us few ions in solution are weak electrolytes, and then examples are listed below. These ones are acidic, and then this is basic. Okay, the others are also acidic. So the only basic example here is this one, the ammonia here. Good. Chemical equilibrium. Now, we'll talk more about equilibrium, so you don't really have to worry ahead here. Most of the examples here will be explained further in the other slides, so we don't have to worry ahead. The only thing that we have to know maybe at this level is that equilibrium will only come in if we have a reversible reaction. And then our reversible reactions will come in if the dissociation that we are talking about is a partial dissociation, such that the ionized species here and then the unionized ones are in a balance. That is when we talk about equilibrium, right? And then the equilibrium will help us calculate for the equilibrium constant. The general formula for equilibrium constant is that K is equal to the concentration, the product of the concentration of the product. That is, if I'm taking this one, these are the products of the reaction, these are the reactants of the reaction. The K, it will be the concentration of the A3O plus multiplied by the concentration of the A minus all over the concentration of the HA multiplied by the concentration of H2. So something like this. So always we are saying that generally the equilibrium constant is equal to the product of the concentration of the products over the product of the concentration of the reactants. Very important. And then maybe general chemistry that we have to also keep is that the K is constant. Equilibrium constant is only constant at a particular temperature. That's if we change the temperature, the value of the constant would also change. Now, let's delve into the main topic, acids and bases. These are products on the market that contain acids and bases. We can analyze the materials when we buy them from the market. Now, these are general properties, physical and chemical properties about acids and bases. And we are saying that acids are sour to taste, bases are bitter to taste. Acids turn blue litmus paper red, bases turn red litmus paper blue. Acids will neutralize bases. Bases will neutralize acids. I think these ones make sense. Now, this is a chemical property. This one is a chemical property. This is also a chemical property. Now, this one here is a physical property. This is a physical property. Arguably, this one is torn between chemical and physical, but then most reference material will place them under physical properties. Good. Now, the next one here is a chemical property. That's metals liberate hydrogen gas on reaction with, acids liberate hydrogen gas on reaction with metal. So then if you have a metal like zinc and then you put it in HCl, we are expecting the reaction to be like this. We form our zinc chloride plus hydrogen gas. We can balance by putting 2 in front of this. This hydrogen gas will be involved. And so always we know that if a metal reacts with an acid, we get an evolution of what? Hydrogen gas. Good. Now on this side, we are seeing that bases are soapy to touch. Now I realize that these two, they don't really correlate. So other reference will say that bases are soapy to touch, and then acids are sticky. Acids are sticky to touch. Very simple. Good. Now we are seeing that acids, aqueous solution of them are good conductors. Bases too, aqueous solution of them are also good conductors. So no problem with that. The last property here is a chemical property. This one is physical. The conduction is physical property. The last chemical property here is that acids decompose metal bicarbonates and carbonates to liberate carbon dioxide. So very simple. We can have something like sodium bicarbonate. Now, sodium bicarbonate plus HCl will give me this. It will give me NaCl plus water plus carbon dioxide, right? This is one of the chemical properties. Now, the same for bicarbonate. If I have sodium bicarbonate and I react with HCl, I am getting similar products, right? So you should know that one of the chemical properties of acid is that when they react with carbonates and then bicarbonate, they will produce carbon dioxide, which will evolve as effervescence. Effervescence. Good. Now, acids and bases have been defined by many people. These are the three. These are not the only definitions that we have, but then we are considering the Arrhenius theory definition of acids and bases, Bronsted-Lowry definition of acids and bases, and then Lewis definition of acids and bases, and then we'll take them one after the other. So Arrhenius. Now, Arrhenius explained acids and bases based on their behavior in water. He realized that if you put an acid in water, it will produce excess of a particular ion, which we call the H plus ion, which we call the proton. And then when it's coordinated to water, we have H3O plus, which we call the hydrozonium ion, And so he said that an acid is any substance which, when placed in water, will produce excess H plus ions, produce excess protons, or will produce excess hydrozonium ions. Same terms. Good. Now, he also said that a base is a substance which, when placed in water, that's aqueous solution, will produce excess of hydroxide ions, right? So he noted his definition based on how they behave in water, and that was one of the limitations, because you bear with me that water is not the only solvent that we have, right? We have many other solvents but water. And so if you define your term based on water, it means that you are limiting me to only water, which is a major drawback of the Arrhenius theory. And then his definition was only restricted to compounds that can produce H plus and then compounds that can also produce OH minus ions. But then there's not all the acids in the world that can produce H plus and OH minus ions. This is an acid, Al3 plus an acid. In a compound form, we have AlCl3. It's an acid, and then it doesn't produce H plus. It has a different way of behaving as an acid. And then this definition wasn't able to capture it. So that becomes one of the limitations of Arrhenius. The next one is Bronsted and Lowry. These are two different scientists. Bronsted and Lowry are two different, but then they sat down and they coined the definition together. And that's why we call it the Bronsted and Lowry concept. Now, he defined, this is the simplest definition of acid that you can find. An acid is a proton donor. He said an acid is a proton donor. Now, the proton he's talking about is the H plus ion. He said that he's saying that if any substance has an ability to donate an H plus ion, then we can call that substance an acid. And then he said that a base is any substance that can accept H plus. So then the one donating is the acid, the one accepting the H plus is what? Is a base. Now, this equation is throwing light on whatever they said. And so you realize that this is ammonia, this is water. Now, this is ammonium ion and this is hydroxide ion. Now, what has happened? The ammonia here has changed to the ammonium here. What specifically is the change? Realize that we have 1 nitrogen here and 3 hydrogen. Now, when we come here, we have 4 hydrogens and a plus here. What has happened is that the water here has given one of its hydrogen to the ammonia, therefore making the hydrogens of ammonia 4, right? And so the water is donating H plus to ammonia. The water donating becomes an acid. The ammonia receiving becomes a base, right? So that is what they said, that the one donating, the proton donor is the acid, and then the proton acceptor is the base. Good. Then the new term that you see here will be conjugate acid and then conjugate base. We have a concept. From their concept, a new concept arose, and that was the conjugate acid, conjugate base pair. It's very simple. Now, it said that if we have a base here, this is the base, right? Now, after the reaction has occurred, the new form of the base here is its conjugate acid. So this was our base, right? After the reaction, it turned to this one. Now, this will become its conjugate acid. That's what we have here. And the two, we call them conjugate acid base pair. Now, the water was like this initially. After giving the H plus ion, it became OH minus ion. So OH minus ion. Now, this is also a conjugate acid-base pair, where this is the acid, and then this will become its conjugate base. Very simple. So now this theory also has limitations. What are these limitations? The first one that is that just like Arrhenius, the scientist wasn't able to explain how compounds like these ones can behave as acids. He couldn't explain the acidic nature of these ones. And then because he was talking about donation and then acceptance, the only thing or one of the things that we can also say is that it was talking about defining the acids and bases when the other partner is around. Because you are telling me an acid is a proton donor. Now, if there's no acceptor, they can't be a donor, because what is the donor given to? So then if I have a solution with maybe HCl, right? With HCl, and then there's no base to accept it. If it dissociates into this one, is it donating? Can you call it as donation? No. So then they define their concept on the fact that a base will be there when there's an acid there. Like they define it in pairs, a donor and an acceptor, right? And then that's another limitation, because you are supposed to be able to define an acid on its own and a base on its own. But then they explain it. That's what this statement means, that this theory explains the behavior of an acid only when there's a base, and then it also explains the behavior of a base only when there's an acid, which is one of its limitation. Now, the new thing in red here says that along with Bronsted-Lowry concept of a proton donor and a proton acceptor arises the concept of conjugate acid-base pair, which has been explained here. Good. Now, this is an exercise for us to try. Very simple. We have bicarbonate ion reacting with water, and then it's forming hydrozonium ion and carbonate ion. Good. Now let's look at the change that has occurred to the individual reactants. So this one bicarbonate will change to the carbonate here. Now you realize that it has lost the hydrogen that it had initially. And then where is the hydrogen? The water here has changed to the hydrozonium ion. Realize that the hydrogens here were 2, now is 3. So then it has accepted an H plus from this one. And so it makes this one the acid, right? Because donating the proton, and this one is the base. The water here is the base. Good. Now, because it's the acid, the new form here will be the conjugate base. Because it's the base, the new form here will be its conjugate acid. Very simple. Now we come here, is the same reaction, the same reactant, but then what is happening? Water has given H plus to the bicarbonate ion, such that the bicarbonate ion has turned into carbonic acid here. Carbonic acid here, and then the water has turned into hydrozonium ion. Now we just have two concepts to explain here. The idea is that now for a reversible reaction, the condition of the reaction will determine where the reaction will go to. And so these are the same reactants, and then we are forming different products. Why are we forming different products? Because these reactions are occurring under different conditions, right? Good. And then you realize that the same particle or the same molecule that was an acid here is also acting as a base here. Now, how is this possible? Water was acting as a base here by accepting a proton. Now, water is also acting as an acid here, giving a proton to the bicarbonate ion. Now, bring that leads us to a principle called amphoterism. Ampho means both. You realize that there's the word ampho in amphibian, many other words, right? The ampho here means both. So we have compounds that can act as acids and bases depending on the condition of the reaction. And then we call those amphoteric molecules, as has been illustrated above. Water is an example, and then bicarbonate ion is also an example. Now, acid-base conjugate pair. We've talked about this already. So this is the nitrous acid. Nitrous acid, a weak acid, will donate H plus ion, and then will form the new form here will be its conjugate base. This is ammonia. Ammonia is a base, a weak base. It will accept a proton and then form the ammonium. Right. So this is the base, and this will be the conjugate acid. The conjugate acid. Very simple. Very simple. So then we are saying that if we have the acid and then it reacts with water, right, the acid will go and form the conjugate base after giving its hydrogen to the water. Now, if you have a base and then it's reacting with water, the base would become a conjugate acid, or form its conjugate acid after accepting the H plus from water. After accepting the H plus from water. Good. Good. So that is that for that. Now we have an exercise to do. We are asked to provide the conjugate acid-base pair in the reaction. Now, perchloric acid is a strong acid, a strong electrolyte for that matter, and then you realize that there will be a small chain between the perchloric acid and then the formic acid. So we are showing their acid-base conjugate pair when they dissolve in water. Now, perchloric acid will dissolve in water to give me, so aqueous, to give me H plus and then ClO4 minus. So then this is the acid and this will be the conjugate base. This will be the conjugate base. There's another way of writing the same reaction. That is HClO4 plus water. And then that will give you H3O plus and then plus ClO4 minus. The same thing. So this is the acid and then this will be the conjugate base. We can also say that this is the base and then this will be its conjugate acid. It's a base because it's accepting a proton from here in this case. Very simple. Now the next one is formic acid. Formic acid will dissociate partially. And so you know the difference between this one and then this one. The perchloric acid, the strong acid, it dissociates fully, and so we use a full reaction sign. The formic acid and organic acid is a weak acid, and therefore dissociate partially. So we use the reversible reaction sign to give me the metanoate ions plus, or the fomate ions plus the proton, right? And then this will be the acid, this will be its conjugate base. The same reaction can be written like this, plus water, and then our reacting reversibly to form the hydrozonium ion plus my fomate ion. Very simple. Good. So the solutions are here. Very simple. Now the next question. Ammonia reacts with water to form ammonium ion and hydroxide ion. So this is the reaction. Ammonia plus water giving me ammonium and hydroxide ion. I am supposed to identify the conjugate acid of ammonia. Ammonia is a base. After it has accepted the proton, it forms the ammonium. So the ammonium here becomes its conjugate acid. Very simple. Now, we are moving to the last definition of acid that we have to talk about in this lesson, as is the Lewis theory. The Lewis theory. Good. Now, the Lewis said that an acid is a species that can accept a pair of electrons, and a base is a species that can donate a pair of electrons. So then, this is ammonia. We know ammonia is a base. Now, ammonia in this case is acting as a base because it has a lone pair of electrons that it can donate, right? A species that donates electron is a base. And then for the Lewis base, because before you can donate a pair of electron, then you should have a lone pair of electron. The lone pair is an electron that you are not using in bonding. And so the nitrogen has 2 electrons here, a pair of electrons that it doesn't use in any bonding. And therefore, it can donate it and then act as a base. We have the BFP, the boron fluoride or boron trifluoride. Now, this is acting as an acid. And then how can it act as an acid? By accepting the electron. How would you accept an electron? You can only accept a lone pair of electron if you have an empty orbital. And so what is happening here is that the boron here has an empty orbital. And then it will use that empty orbital to accept the lone pair of electrons. So then if you write the configuration of boron, this is 1s2, 2s2, 2p1, 5 electrons. Now you bear with me that the p orbital has 3 suborbitals under them. And so one orbital is filled with 1 electron. We have this empty orbital and this empty orbital, which can fully accept the lone pair coming in. And so we realize that all the lowest acids have they have empty orbitals that they can use to accept the lone pair of electron coming in, and then all the Lewis bases have lone pair of electrons to donate. Very simple. Now, when they donate the lone pair, it forms a special type of bonding called the dative bonding. Dative bonding. Dative bonding is same as the coordinate covalent bonding, right? So we form a coordinate covalent bond. Coordinate covalent bond. Very simple. Form a coordinate covalent bond. Very simple, right? And then this theory will account for why AlCl3 is an acid, because the aluminium here, if you write the formula, the configuration, you can write and confirm it has a lone pair, it has an empty orbital that it can use to accept the electron. Now, this theory also has limitations. The limitation is that it couldn't explain then the acidity of compounds like HNO3, H2SO4, which cannot form coordinate covalent bond. Because what is happening here is that we are forming coordinate covalent bond, and that is how the acidity is being depicted. But then these ones cannot form coordinate covalent bonds, right? The HClO4, the HNO3, the H2SO4, they are all strong acids, but then they cannot form coordinate covalent bonds, right? The next one is that now the reaction, the acid-base reaction for Lewis acids and bases are very slow, which is contrary to the fast reaction of normal acids and bases that we have. So then it was one of the things that they couldn't really explain. And then they couldn't also explain the simple neutralization reaction that involves the H+ ion, the one that we know already from SHS, and it couldn't explain. And then it couldn't also explain the strength of acids. So then how strong is boron trifluoride from aluminum chloride? It couldn't also explain that. So that is one of the limitations of the Lewis concepts. Good. Now, the next thing, solvent type. Most of the definitions or generalizations we have made in chemistry as a result of, we can see maybe a salt is insoluble. Usually what we are thinking of is water being the solvent, but then it's not always water that is the solvent. And then each solvent will have different property depending on the solvent we are talking about. We can boldly say that sodium chloride is soluble in water, right? So sodium chloride is soluble. But then sodium chloride is not always soluble because it depends on the solvent we are using, such that if you put sodium chloride in benzene, it will never dissolve. It will still remain as crystals. And so we have to know the solvent types available. And then if we mention a particular solvent, that can give us an indication of the behavior of the solute in that particular solvent. Now a question can come. If I put HCl liquid in CCl4, the HCl will not act as a conductor. But then if I put it in H2O, if I put HCl in H2O, then it can act as a conductor. And then this question should be answered by the time we are done with the types of solvents we have. So the first one, we have protophilic solvent. Now, when we say a solvent is protophilic, two words. Proto is H+ proton, right? And then philic is La for or affinity for. So what we are saying is that these solvents have a La for or affinity for, or then per definition, they have a greater tendency to accept protons or H+. Now, when we mention protons, we are talking about H+. Now then, we know that compound that can accept H+ from the Bronsted-Lowry concept, the proton acceptor or H+ acceptor is a base. So then it shouldn't surprise you, sorry, that we have liquid ammonia here, right? Ammonia is a base. And then if we use the ammonia as a solvent, it will be protophilic. Protophilic meaning that it would love to accept a proton. Now we have water here. Water can also accept a proton. I think most of the reaction we have dealt with so far can give us an indication that water can accept a proton. The next term here is protogenic. Generate. So these ones can generate or produce protons, right? Now, compounds that can produce protons are acids. So then it shouldn't surprise you that we have liquid hydrochloric acid here, and then we have the glacial acetic acid here, right? It shouldn't really surprise you. Now, water also comes here. Water comes here. That means water can also produce protons, and then this shouldn't surprise you because most of the chemical reactions we have dealt with so far have shown that water can donate a proton. Good. Now the next one, amphi. We've talked about amphi already. Amphi means both. Now we have some solvent that can donate protons and also accept protons depending on the reaction condition. They are both protophilic and protogenic, right? And then an example is water. Water is a universal solvent. Water is amphiprotic. That is, it can either give out a proton or accept a proton. Very simple. Then we have ammonia and then ethyl alcohol. Ethyl alcohol is the same as ethanol. Shouldn't be confused. Ethyl alcohol is the same as ethanol. Now, the last type of solvent we have is aprotic solvent. Aprotic solvent. Now, aprotic solvent would neither accept nor donate a proton. And so if you put anything in it, any solute in it, it would not allow the solute to give it protons, neither would it take protons from it. It would make the solute remain as it is. Examples are benzene, carbon tetrachloride, also known as tetrachloromethane, and then we have carbon disulfide. Now let's go back to the question I asked here, HCl in tetrachloromethane. Now I realize that the tetrachloromethane here is an aprotic solvent. Aprotic here means that it will not allow the HCl to dissociate, and so the HCl cannot produce H plus ion or any other ion in the solution. It will not accept the proton, it will not donate the proton. The solvent will not allow it to dissociate, so it will still remain as the HCl liquid with molecules inside, and then the molecules cannot conduct electricity. But then if you put it in water, we talk about water as being protophilic, protogenic, and then amphiprotic. So then water can allow the HCl to give it protons or to dissociate in it, and then it can conduct electricity. Good. Now, the next concept, leveling and differentiating solvent. I feel these words are betraying words because if I say levels, if I say I'm bringing two people to the same level, then it is self-explanatory because then I'm bringing them to the same line or I'm balancing them. That is the idea. And that is exactly what water does. Now, we have strong acids, we have weak acids. The classification of strong acids and then weak acids is because strong acid and then weak acid is because of the extent of dissociation in water, such that if an acid dissociates fully in water, we call it a strong acid, and then if an acid dissociates partially in water, we call it a weak acid. But then what happens if you put any strong acid in water? Strong acid as HCl, right? In water, I'm getting H plus Cl minus ions, right? Good. Now, if I put H2SO4 in water, or maybe HNO3 in water, right? Now I'm still getting H plus NO3 minus. Now in either case, I'm producing H plus. And so if I ask myself which one is a stronger acid, I might not be able to do it or find out because all of them are producing H plus ions. And that is what we are talking about, that in water, the highest acid that we can have is H plus ion, right? And so irrespective of the strong acid coming in and dissociating fully, water will level all the acids or all the strong acids to H plus ion. In water, the highest acid that you can become is the H plus ion, right? And so irrespective of the strong acid coming in, water will level you to the H plus ion. And that's what we call the leveling effect of water. And so let's read the statement here and see whether we can understand it. It said that all strong acids react with water to form the hydrozonium ion, that is upon coordination with water, right? Therefore, no acid stronger than hydrozonium ion can exist in water, right? No acid stronger than hydrozonium can exist in water or aqueous solution, leading to the phenomenon called the leveling effect of water. Water will bring all the strong acid to the hydrozonium ion level. Very simple. Now, in the same regard, water will also bring every base available to OH minus ion. So then if you have NaOH, water is bringing it to Na plus OH minus ions. If you have KOH, water is doing the same thing of bringing it to K plus ion plus OH minus ion, right? Good. So water will level you to OH minus ion as a base, and then the highest base that can exist in water is just OH minus ions, right? And then that's what we call, or that's what we mean by leveling effect. Water will level all the strong acids and bases to the same level. That is either H3O plus or OH minus ions. Very simple. Very simple. right? So then we can read this. That's we are saying that all strong acids have the same strength in water and are completely converted in solution to the hydrozonium ion. Strong bases likewise to the hydroxide ion, right? Now, if you study chemistry a little bit, you know that sodamide or sodium amide is a very strong base, exceptionally strong base. But then in water, if you put it in water, it will be only as good as sodium hydroxide, because water will level all of them to OH minus ions. And that is what we are talking about regards to the leveling effect of water. Now, there's another between word here, differentiating solvent. So the differentiating solvent will allow you to measure the relative strength of the acids and bases that we have put in a solution, right? And so you realize that if we are not talking about water as a media, but then if we are using ammonia as a solvent, then we can actually see the difference between the strength of sodamide or sodium amide and then sodium hydroxide. Water will not make you measure the difference between their strength, but then ammonia as a solvent can help us differentiate, and then it will clearly show that sodamide is a stronger base. And so ammonia here is said to be a differentiating solvent because it can distinguish between the strength of these bases, right? Good. So that's the difference between a leveling and then a differentiating solvent. Good. Next one, solvent effect on acidic strength. I have already mentioned that the solvent you are in will influence your behavior, such that we cannot even say that sodium chloride is always soluble. It is soluble depending on the type of solvent we are subjecting you to, right? And then in this same regard, acids and base strength is generalized in water, but then depending on the solvent we are talking about, an acid might not really be an acid. Let me share a white screen and then talk more on that. Very simple concept. A very simple concept. So then, let me write these random compounds. HCl, NaOH, acetic acid, ammonia, water. Now, these are different solutions available. Most of these compounds have been categorized based on their behavior in water. So then generally we know that HCl is a strong acid, NaOH is a strong base, acetic acid is a strong, a weak acid, and then ammonia is a weak base. We have these generalization because we consider water as the solvent. What if we are not using water? What if we are not using water? And so if I have acetic acid as a base or as a solvent, and then I put HCl in it, what will happen is that because acetic acid is already an acid, and then it can produce H plus on its own, it might not allow the HCl to also fully dissociate and give it more H plus ions. And so it might hinder the full dissociation of the HCl and make it rather dissociate partially. Right? Now, if HCl dissociate partially, HCl is then acting as a weak acid. And so HCl in acetic acid will become a weak acid. It will become a weak acid. Now, why is it acting as a weak acid? Because the solvent here is already acidic and it has H plus ions, and then it will prevent the HCl from dissociating fully to give it more H plus ions. Very simple. Very simple. Right? So it acts as a weak acid. Right? Good. Now, the concept I have just explained here is what we call the common ion effect, which is in the slide. The common ion effect just says that if I have a solution containing an ion like this, maybe the H plus ion. Now, if a compound is supposed to come in and dissociate, right? And then the compound is producing more H plus ion for me again. Because there's already an H plus ion, that H plus ion would prevent the dissociation of that compound to give it more of what it already has. Do you get it? And so that is what we call the common ion effect. And so we are saying that this is acting as a weak acid in this case because of the common ion effect, which is the H plus ion that both of them are given. Contrary to that, if I put ammonia in acetic acid, ammonia is known to be a weak base, right? But then if I put in acetic acid, this is an acid, and it's acting as a solvent in this case. Acid are proton donors, right? They love bases. They can react with bases. And so what will happen is that if the ammonia is supposed to give OH minus ions to the acetic acid will not allow the ammonia to dissociate partially. It will make it, or it will force it to dissociate fully so that it can abstract more OH minus ions, and therefore force the ammonia to act as a strong base. And so you realize that the ammonia will be a strong base in acetic acid as a solvent. Very simple. Let me change the solvent. Now, assuming I have ammonia as a solvent, right? If I have ammonia as a solvent, if you put acetic acid inside, which is a weak acid, now because this is a base, it will force the weak acid to give it more H plus ion. That is, it will force it to dissociate fully, and therefore the acetic acid here will be a strong acid, right? It will be a strong acid. Now, if I have a solvent like HCl, if HCl is a solvent and then I am putting acetic acid inside. Now look at this. This is an acid. This is an acid. This is a solvent, right? But then this solvent here is a stronger acid than this one. And so if we put the acetic acid in the HCl, what will happen is that instead of the acetic acid dissociating as an acid and then giving me H plus ions, the HCl, which is the solvent, will rather give it H plus ion because it is stronger than it. So the H plus ions will move from here to here, forcing the compound to form an ion like this. It will force it to form an ion like this, right? And so in that case, because the HCl is forcing the acetic acid to receive the H plus ion, it is acting as a weak base. Strangely, it is acting as a weak base. That means the acetic acid is not always acidic. It is acidic depending on the solvent we are using. And if it happens that if you are using a solvent which is stronger than it in terms of its acidity, it would actually force it to accept and then act as a base. Very simple. So that is what we mean by the solvent effect on acidic strength. I think we can read more on that in the slide. Moving on. So these are acids and then their names. Very simple. If you know them, it will help you. These are strong acids. The strong acids we have around. These are the weak, the strong bases we have around. And then we consider them as strong or weak depending on their dissociation in water. And then they dissociate fully in water. That's why we call them strong acids, strong bases. Very simple. Very simple. Very simple. Solvent effect on acidic strength. The acidic strength of a weak acid is enhanced by a strongly basic solvent, and the basic strength of a weak acid is enhanced by a solution of strongly acidic solvent. I think I've talked about all these ones, so it's fine. Good. Weak acids. Now we see an acid is weak if it dissociates partially in solution. Partially in solution. What solution are we talking about? Water as the solvent, right? Good. And so we realize that the hydrocyanic acid, or the hydrogen cyanide, and then nitrous acid, and then hydrofluoric acid, all these are weak acids. All these are weak acids, right? Now, these are inorganic acids which are weak. We have organic ones. All the organic acids that you can find around are also weak. So the acetic acid, the formic acid, the metanoic, the propanoic acids, all of them are weak acids. Good. Now, because they are weak, they dissociate partially. Now, the partial dissociation or the reversible reaction would bring something that we call equilibrium. Equilibrium. So, equilibrium. So, this is a scenario. We have HCl. Now, HCl will dissociate fully. So, we use a full reaction sign here. There's a graph or a picture that's showing us where strong acid will always dissociate fully to give H plus ion and then A minus ion. That is if the acid is HA. Right. So, we realize that there's a full dissociation produce a lot of ions. That's 100% dissociation. Should it happen that if the acid here is weak, it dissociates partially to give only a few ionized sample and then a lot of the unionized ones. And then look at this arrow. It will happen such that the ionized one and the unionized one are in a dynamic equilibrium. So we'll talk about the equilibrium more. But then what we have to note here is that there's very little dissociation of the ions. Very little dissociation of the ions. Good. So then let's talk about our first. Let's deduce the equation. Let's share a high screen and then deduce our equation. Good. Good. So yes. Now, assuming this is a weak acid HA plus H2O, it will react reversibly because it's weak to get H3O plus A minus ions. Now, I've already explained the principle behind the equilibrium constant, which will be K. Now, the K will be the product of the concentration of the product over the product of the concentration of the reactant. So then we have H3O plus concentration multiplying A minus concentration all over HA concentration and then the concentration of water here, right? Now, one thing we've realized about this equation is that water is a solvent for all of the acids. So it is usually in excess, right? It's in excess, and then we feel that it's fairly constant in the reaction. It's constant. So what we do is that we remove the water here and then we multiply it. So if I'm canceling out GHS, I'll multiply this side by water, this side by water. Very simple, right? Good. So this one can cancel out this water. So then I have K multiplying the concentration of water, which we know is fairly constant, and then it's giving me H3O plus concentration A minus concentration all over the HA. Right? Good. Now the whole of this is what we call the KE. It's what we call the KE. So the KE expression captures this. That's K is equal to concentration of the H3O plus multiplying concentration of the A minus all over the concentration of the undissociated acid. That is the key. The key is called the acid dissociation constant. The acid dissociation constant, right? The acid dissociation constant, a very important term. Now, for now, what we have to know is that, let's explain this. Now, the fraction here has the ionized PC as the numerator, the unionized one as the denominator. And so if it happens that Ka is equal to 1, it means the number of the ionized PC is equal to the number of the unionized PC. Very simple. If the Ka is greater than 1, it means the numerator here is bigger than the denominator. Because if you have a bigger number as a numerator, then we have a number which is more than 1. Good. Then if the Ka is less than 1, it means that the undissociated one is more than the dissociated one, right? The undissociated species is more than the dissociated one. So then it means that it is, let me change my ink to green. Okay, so that it means that it is weak. And then most of the weak acid will actually behave like this. The Ka will be less than 1. The Ka will be less than 1. Now, Ka is significant in pharmaceutical chemistry. That Ka will tell us the extent of dissociation of the acid. Now, you realize that if the acid dissociates more, it will produce more of the ions. Which of the ions are we talking about? The H plus ions in solution. Now, if you produce more H plus ions, you are more acidic. And so we see K is directly proportional to the acidity of the compound. That is, the higher the K value, the higher the acidity. Right? The rationale is that once you have a higher K, it means you ionize more. Once you ionize more, it means you produce more H plus in solution, more H plus in solution, right? Very simple, very simple. Now we'll introduce ourselves to a different concept called the pKa. Let me comment on that before we move on. The pKa. Now the pKa is equal to the negative log of Ka. Put this in your head in chemistry. If you see the P in equations, it's negative log. So negative log is just P. So then you see pK, you see pH, you see pOH. The P here is just negative log, right? Negative log, very simple. Good. So now the pKa, unlike the Ka, is inversely proportional to acidity. Inversely proportional to acidity, right? Such that the higher the pKa, the lower the acidity. The higher the pKa, the lower the acidity. Very simple. Let's go back to our slides and then continue from there. So then I've explained how we came about this equation, right? Good. Good. So they have given us a general statement: the smaller the constant, the less the acid ionizes, and the weaker the acid. I think this has been explained already. Now, this is a behavior of a polyprotic acid. Now, what do we mean by polyprotic acid? Polyprotic acid. The protic is just protons, right? Poly means more than one. So any acid that can give us more than one proton is called a polyprotic acid. The example cited here is H3PO4. Now we are saying that if for any acid that can give us more than one proton, the giving of the proton is in bits. We don't give all the three at a go. So it will give the first one, the second one, and then the third one in different succession. And so you realize that this equation captures the first time it was given an H plus. This captures the second time that from the ion form, give the second H plus. This is the third time it's given the H plus, such that it has no H plus again. Now you realize that the Ka for each step is different. That is, the ability of the next species to ionize is different. That is, the ability of this one to ionize is different from the ability of this one to ionize, right? Now, if you study very well, you realize that the first ionization constant is bigger than the second one, and then it's bigger than the third one. That is, after the first ion has gone into solution, the ability of the next ion to dissociate again reduces. That is, the acidity reduces. Now, generally, it is reducing because of what we call the common ion effect. Because you bear with me that after the first one has gone into the solution, after this one has gone into the solution, right? Now we have H plus in solution. This one is supposed to dissociate to give me more of the H plus. Because we already have H plus in solution, it will prevent the dissociation of this one to give you more of the H plus again, right? Good. Now, because in this case too, we have more of the H plus again, it will further prevent this one from dissociating to give me more of the H plus again. So you realize that the acidity, right, of these species as they go about their successive donation of the proton will decrease. And so always realize that the Ka1 is greater than the Ka2, it is greater than the Ka3. Very simple. Very simple. Now this is a table. We have some acids, their formula as against their successive Ka values. Now you always realize that the Ka1 is bigger than the Ka2, showing you that the ability of the solution to accept more H plus decreases because of the common ion effect. Now, one thing which is really noticeable here is the H2SO4 here. Now, H2SO4 is a strong acid. Now, it gives two hydrogen ions. These hydrogen ions are not given at a go. They are given in succession. And so you realize that for the first donation of the H plus ion, the Ka is very large. It's 100. 1.0 times 10 is about positive 2. 100, right? Very large. But then the second one, the Ka has reduced to 1.2 times 10 raised to the power -2. That shows you that the ability of the solution to accept H plus now is very low. It's because it already has H plus in the solution. Because it already has H plus in the solution. And so in the first instance, the H2SO4 is acting as a strong acid. In the second instance, it is acting as a weak acid. Right? So that's the ion is acting as a weak acid. Good. Now, for bases, it's the same thing we are talking about. The same concept we are talking about, right? The same concept we are talking about. So, assuming this is a base, if you manipulate it just as you manipulated the acid, you come and get, or you arrive at this constant, right? And then the Kb will be the base dissociation constant. The Kb is also directly proportional to the alkalinity of the base, or the basicity, which is quite arguable a term because it can imply something else, right? Good. Now, if I have a higher Kb, I am better off a base than you are. Very simple. Very simple. Very simple. So we should take note of that. Now, this is a specific example for one of the species. Ammonia in water gives me ammonium and then hydroxide ion. If I want to write the Kb expression, it should be the concentration of the product multiplying each other. So NH4 plus then OH minus ions all over the ammonia. We don't bring the water because water is in excess, right? Water is in excess. Very simple. Now we are seeing that the Kb of this one has been predetermined, and then it's 1.8 times 10 to the power -5 at 25 degrees Celsius. Equilibrium constant should always be stated at a particular temperature because the value will change once the temperature changes. Good. Now this value is very small. Now it being small actually tells us that the dissociation is very small, right? Dissociation is very small. The ammonia might not really dissociate to give you a lot of OH minus in solution. No. 10 raised to the power, 1.8 raised to the power, 1.8 times 10 raised to the power -5 is really a small number, 0.000018. That is a small number. Now we are saying that the larger the Kb, the stronger the acid. That has been said already. The next thing is that the pKb will turn it upside down. So then the larger the pKb, the weaker the base. Now we have a question to solve here. The question says that consider these two acids and their Ka values. So we have HF and then HClO. Now, mind you, HClO is different from HClO4. HClO4 is the perchloric acid, is a strong acid. The HClO is a weak acid, so you shouldn't be confused between these two. You shouldn't be confused between these two. Good. Now, we have the Ka values, and then we have to compare. Now, you know that the higher the Ka value, the higher the acidity. And so which one has a higher Ka value? This one has a higher Ka value, the HF. Therefore, the HF is what? Is the stronger acid. Good. Now, percentage ionization of a weak acid. So we will end our first video here. We are doing it in bits. So you stay tuned for the second one. If you have any question, you contact any member of the academic board. Contact any member of the academic board, and then please, if there's anything contradictory between what is said here and then what is said at lectures, please follow the lecturer. Thank you very much for your audience, and then have a nice day. Bye.